Let's get started with question 1319, number of operations to make a network connected. There are n computers numbered from 0 to n-1 connected by Ethernet cables connections, forming a network where connections of I equals A, B represents a connection between computers A and B. Any computer can reach any other computer directly or indirectly through the network. Given an initial computer network connections, you can extract certain cables between two directly connected computers and place them between any pair of disconnected computers to make them directly connected. Return the minimum number of times you need to do this in order to make all computers connected. If it's not possible, return -1. So let's see this example. It's given here that 0 is connected to 1 and 2. So there is an edge between the computers 0 and 2. That is, there are cables attached between 0 and 2. 0 and 2 and 0 and 1. And 1 and 2 are also connected. So we can just extract one cable from 1 and 2 and put it between 1 and 3. So the network here is connected. So second example is also similar, and seeing these examples, third and fourth. In third, it's given that you cannot connect this network, that is the output is -1. So why do you think is that? Well, let's see. First of all, you are given this chart here where the nodes, these are the nodes which has the numbers in it 0 to n-1. So you are given this connections here. So let's count the number of connections first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 connections. So now I want to pause this video and see for yourself if you can connect this entire system through these cables. I would like you to pause the video now. So, were you able to connect the computers to one network? I guess not. Let's see for ourselves. First, let's remove some cables like this one here, this one here, and this one here, so that we don't disconnect the already connected computers to the network. So if I remove any cable from here, the computer here would be disconnected from 9, and if anyone from here, it would again be disconnected from 0. So we cannot remove more cables or the computers would be disconnected. So we have 3 cables as we have removed 3 cables. So let's try connecting the structure. Let's put one cable here and one here and one here. So we can see that this huge component has been connected, but still these 2 computers and this one computer is disconnected from the main network. So how many minimum number of cables do we even need to connect this entire network? Well, what if I told you to keep these 13 computers, that is 0 to 12. So we have 13 computers, so put these 13 computers in a line. So how many minimum cables would you need to connect it to the network? That is, you can put each cable between each pair of computers. So how many minimum cables you will need? Well, if you could guess, the answer is 12. That is, if you have 13 computers, you will need 12 cables. So if you have n computers, you minimum need n-1 cables to connect all of them, else it won't be connected. So it is not compulsory that we connect it in form of a line only. We can connect it in form of a graph. Now, a graph is a connected data structure, and if you don't know anything about graph, please see the link in the description and read some points about graph. And in a graph where all components are connected only once, that is, there is no cycle in a graph, it is called a tree. And in a tree, for n nodes, there are n-1 edges. So we can connect this entire network in form of a tree. For example, we can connect it like this. 4 is connected to 5, and here 3 is connected to 6. So now you can see that every computer is connected to every other computer. Like if we wanted to go from 7 to 9, we would choose this path here. So every computer is now connected to the network. So let's count the number of edges. That is 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12. So yeah, you will need 12 edges to connect 13 computers. So if you have less connections than n-1, then you can never connect to the network. So we now know the condition where our answer will be -1. So how to solve this question now? Now we are going to assume that we have at least n-1 cables or edges. So first of all, let's erase this new graph and get back to our old one. So here there was no connection here and here, and now we had this edge here, this edge here, and let's add 2 more edges for, at least we should at least have minimum number of edges. So we can connect 1 edge here and 1 edge here, and we can also add 1 edge here. So our total number of edges are equal to 13 now. So we have 13 computers and 13 edges. As the edges are greater than or equal to 12, that is n-1, we can connect this network. So how are we going to solve this problem? Well, first I said that this connection is like a graph. So if you know graph, you can traverse a graph in 2 ways. First, depth first search, and second, breadth first search. We will be using depth first search in this question. So if you want to read about depth first search or breadth first search, you can refer to the link in the description. So how are you going to solve this using depth first search? Well, we will first make an adjacency list. Also, you should know what an adjacency list is. Basically, it is a 2-dimensional matrix. Well, actually that would be an adjacency matrix, but here we use an array of vectors to represent a list. For example, we have the input is given in this format. For example, we have node 0 and the connections here are 1 and 2. So we at index 0 in a vector we store 1 and 2 to denote that 0 is connected to 1 and 2, and similarly for another node, for example 1, it is given as 1 is connected to 0 and 3. Also, this is an undirected graph, so there are no directed edges, so we will consider connections on both ends. And one more, for example, here we are given 9, for example. So 9 is connected to 8, then 10, then 12 and 11. So this here is called an adjacency list. That is, the adjacent nodes are stored in a list. So first we will be creating an adjacency list of this entire graph. So let's create it actually. So we have for 0, for 1, and then we have for 2, or actually it would be tedious, so you can create the rest of the list yourself. So we have this list here. So we can, like, for the purpose of representation, we can just see the diagram here. So what are we going to do in depth first search is that we will go in depth until we can go in no more. That is, for example, let's take the node 0. If we come on node 0, then we will see what is directly connected to node 0, that is node 2 and node 1. So first we will be traversing node 2, and then before even traversing node 1, we will see what is connected to node 2. So we will see node 0 and node 3. As 0 is already visited, so we won't visit this node 0 again. we will just visit node 3, and then we will see 3 is connected to 2 and 1, and we know that 2 is already visited, that is, we already have visited 2 and came to 3, so we won't visit 2, we will directly go to 1, and then we will see 1 is connected to 0 and 3, so we will get back in the recursion. And yes, we will be applying DFS, that is depth first search using recursion. So we are on 1, we see that both these nodes are visited, so we move one step back, we come to 3, we now see that both these nodes are visited, so we again move back in recursion, we come to 2, both nodes are visited, then from 2 we come to 0, and finally we exit the recursion. So now we have traversed this entire connected component. This here is called one connected component, this here is one connected component, this here is one, this here itself in itself is one connected component, and this here itself. So let's also see this example. So for example, we are on node 9. So in 9 we have in list 8, 10, 12 and 11. So first of all we will traverse to 8. So let's keep the track. From 9 we traverse to 8, and we see that 8 is connected to 10 and 11. So both are not visited, so we can visit either of them. So let's visit 11 first. So from 8 we go to 11. Now we see that 11 is connected to 9 and 8, and 9 and 8 both are visited, so we move back in recursion. So after visiting 11 we move back to 8, and then as 8 is connected to 10 we move to 10. So now we are on 10. On 10 we see that 10 is connected to 8, 9 and 12. So as 8 and 9 both are already visited, we won't visit it again, and we will move to 12. So 10, we will move to 12. So we are on 12, we see that 9 and 10 are already visited because they are connected to 12. So as they are visited, we will move back in recursion. So we are on 10, we see that 8, 9, 12 all are visited, so we again move back. On 8 we see that all the nodes 11 and 10 are visited, so we again move back. In 9 you also see that all the 4 nodes, that is 8, 10, 12 and 11 all are visited, so we again move back. So we have visited each and every node here in this connected component. Similarly we will do for 6, 7, 4, 5. So what can you see? So we can make one observation here, that when we start from 0 we can traverse all these nodes and mark them visited. Now if you are wondering how are we going to track the visited nodes, we will be using an boolean array to identify if the node is already visited or not. So we will be using DFS on this node. So when we use DFS, all the connected nodes are marked visited, and when we use DFS on 0, 1, 2 and 3 will be visited. When we use DFS on 1, as it is already visited, we actually won't use DFS on 1, and on 2 it's already visited, so we won't use DFS. 3 we won't use. Now 4 we will use DFS, so we will go on 4 visited and see that it has no connected nodes, so we will again come back, and so on. So we now see that we will have to traverse in DFS. Like, I'm talking about calling DFS function, not actually traversing. So we'll have to call the DFS function 1, 2, 3, 4, 5 times. For one for this, one for this, one for this, one for this component, and once for this component. Because when we call DFS for this one component, this node will in turn call the DFS for all these other components. So the number of times we call the DFS is the number of connected components we have. So when we call DFS for this and this, we will call DFS 5 times. So we have 5 distinct connected components. That is, one is this component, one is this, and this. So now we need to connect 5 components using how many cables? Well, you guessed it right, 4 cables. So we will need 4 cables to connect these 5 components. So you know that if the cable is less than n-1, we cannot connect the components. But if the cable is greater than n-1, where n is the number of nodes, greater than or equal to n-1, then we can connect it. So we only need to check how many connected components are there. First of all, we will check if the number of connections are equal to or greater than n-1, or more clearly, we will check if the number of connections are less than n-1, so we will return -1. Else, we will check the number of connected components. Here we have 5 connected components, and return components -1. That is, number of connected components -1. As we have 5 connected components, we will need 4 connections between them. So minimum number of cables we need to remove from these connected components will be 4. Let's try it out. First, let's erase this cable, for example, and one this and one this cable. So removing these 3 cables, and actually we will need 3 and 4. So let's remove one more. So we have removed 4 cables right now. So let's connect these 4, 1, 2, then we connect this 3 and this 4. So you can see that all the components, that is all the computers, are now connected to a single network, and the number of cables 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's right, we need 12 cables to connect 13 computers. That is, we will need n-1 cables. So if you have understood this, let's code this approach. So first of all, we will check the base condition that if the connections itself are less than n-1, then there is no way we can connect the entire network. Then we create, that is, we define an adjacency list. That is an array of n elements where each element is a vector. That is, a vector is a resizable array, so we can store as many connections as we want. For example, here we iterate through the connection matrix, that is vector of vectors. So if you can see here, for example, we take this 0 and 1. So we will do g of 0, that is at index 0, we push back in the list, that is we insert at the back of the list what, this number 1, and for this g1, that is for index 1, we insert at the back of the list 0, so that 0 is connected to 1 and 1 is also connected to 0, because this graph here is undirected. So here we create the adjacency list, and then we created the visited array. That is, it will keep track of all the nodes that are already visited. So initially we initialize all the elements in the array to false because none of the nodes are visited, and then we define a com variable which will store the number of distant connected components. For example, here we had 5 distant connected components, so it would have stored 5. Now for the rest of the code, we will iterate through each computer. That is, we will iterate through 0 to n-1. That is, each computer will be iterated, and we will check if it is already visited through the visited array. So if the computer is not already visited, the value would be false and this would be executed. Now for each computer, if it is not visited, DFS will be applied to it, and the number of times DFS is called will be the number of distinct connected components we have. So for example, I is 0, so here I is 0, so this 0 will call DFS in return for 2, and 2 will call DFS for 3, and it will come back, and 0 will again call DFS for 1. So 0 will call DFS for 2 and 1, 2 will call for 3, and so all these nodes will be visited. So if I equal to 0, this will be first executed for I equal to 0, for I equal to 1, as DFS was already called at I equal to 0, DFS won't be called for I equal to 1, 2 and 3. Then for 4, it would be called. For 5, condition visited as 5 is not already visited, it will again be called. 6, not visited, 6 will call DFS for 7, so here DFS for 7 will not be called. So till now we have called for 0, 4, 5 and 6, so we have called 4 times, and then for 7 we won't call DFS, and for 8, this 8 will in turn call DFS for 9, this 9 will call for 11, 12 and 10. So this all of these computers will be visited when we visit 8. So we call DFS for 0, 4, 5, 6 and 8. So finally we call DFS for 5 computers. So we will have 5 distinct connected components. As you can see here, 1, 2, 3, 4 and 5. So we have 5 distinct connected components. So the comp here would be incremented each time this condition is true, so the value of comp will be 5, as it will be incremented by 1 5 times. So finally comp is equal to 5, and how many cables do we need? How many cables do we need to connect 5 distinct connected components? Well, you can guess it. Yes, the answer is 4. For connecting n computers, we need n-1 cables. So for connecting n, that is here COM connected components, distinct connected components, we will need COM-1 cables. So this is the code for connected, and for the DFS part, this here is the code for depth first search. So first of all, when we go in the node, we mark it as true, that yes, we have visited this node. Then we iterate through the neighbors of this node, that is from g of x comma I, we iterate through all of these neighbors. That is, for x equal to 0, we will go through 2 and 1. So 2 and 1 will be visited here, and that 1 would call 2 in return, and so on. So every connected node would be visited by DFS. So this here is the code for DFS, and this here is your code for finding the number of cables. So that's it. Hope you understood this approach. Thank you.